tiny.
Okay.
Let's start. Hello. Good morning. So I propose that today we spend all the time necessary on this Excel sheet because it is including the important part of the analysis of the feed of the furnace. It is including the mass balance, this part, and then it is including the energy balance, and then it is also including something which is a very easy, which is it is the calculation of the tapping sequence. But this part is, is an example of what you can do, but you can also change it and make other calculations. So what I say is this part is not so important. It can be done separately. I suggest that we begin with ferromanganese. So you've got two files. So this is the ferromanganese file. And maybe just a small comment before starting. For sure you know what's an Excel sheet, but I would like to emphasize that an Excel sheet is not different from what you should be able to calculate manually on a sheet or on the board. So the result of an Excel sheet is finally the result of a calculation that you give to the file, and so the quality of the calculation is the quality of what you give in, and the quality of your assumptions. Do you agree?
동영상 중에 정신을 딴 데 두고 있어.
예?
얘기하는 거 듣고 눈을 보고 마주치고 얘기해야지. 전부 노트북 다들 한다니까 그냥 준 거 이거지 뭐.
You should never forget that today I will explain in detail how this is done. But afterwards, each time you calculate, you must not imagine that I put some data and I have the right result. As I insisted yesterday, the assumptions you make, and you will see there are 10 or 20 or more cells where you make, when you put a figure in, you make an assumption. And that is not written on the sheet, but it is then your responsibility to make a good calculation or not a good calculation. I mean, what I can give you, what I explain you today, is a method, and I will point out some difficulties and some assumptions that are key assumptions. But afterwards, each time you use it, you have to think about: is this the good assumption? Is this a good way to do it? And you will see when changing the family of furnace, when moving from the ferromanganese to the ferronickel, there are some assumptions that are different. And even sometimes you add some cells or you scrap some cells, because each case has to be thought in detail for all figures you build in. Okay, that's a short introduction. So let's begin with this. First, there is a part, this part, which is actually not, which you don't need absolutely, because I just put here as a memo the data that you give me, which are the input data in terms of ore, coke, and dolomite proportions and moisture of each. So you see, what you sent me are these three data. These are the data of charging proportion: 75% ore, 13% coke, roughly 12% dolomite, and the dolomite including 40% MgO, 60% CaO. The moisture of each for the coke, for the ore, for the coke. Of course, dolomite is dry, must be so. And here you have the first calculation, just transforming the proportion here into proportion dry and compared to the dry ore being 100. You understand? We will see how it's done.
More to explain the percent dry,
Yes.
dry ore.
Yes, yes. Every balance you do, every analysis, when you analyze your ore, you take a sample and you first dry it. So the analyze we're going to put in is on dry ore. And of course, in the balance, you must consider the moisture. We will consider it. But we have dry ore in the analysis. And also, when you make balances, you normally start with 100 kilo or 1 ton, or 100%. So it's convenient to know what is the proportion of coke versus for 1 ton or for 100 kilo dry ore, how much coke, how much dolomite for 100 kilo dry ore. And this is only the proportion of coke calculated. It is, you see, it is this figure divided by this and corrected by the moistures.
다 이해했어요? 응?
So it is
거기서 이해했어? 이해 못했으면 질문을 하고 적극적으로 해. 이해를 해야지. 제일 이해를 해야 될 거기서가 이해를 가만히 있으면 어떡해.
Would you explain more detail?
I explain more in detail. First, a general remark. On this sheet, everything can be changed, but until now, on this sheet, the yellow cells are input cells. Generally, it's like this. So, this is input. This kind of yellow, this is not. Okay.
In this case, we change this yellow cell. We can change only yellow cell.
Yeah.
The other brand line, for example, the moisture percent is 3.3. Is some cases.
Is that is input data also? You should make it in. You should put it in yellow as well. Yes, you're right.
지금 일반 광석 자체를 드라이한 상태로 전부 전환해주는 과정이라고 하냐? 기본적으로?
Let's put it.
예? 아니요, 광석 자체를 100%로 놓고 지금 코크하고 돌로마이트를 분율로 나눴는데 그 계산이 좀
계산 말고 좀 얘기하는 걸 들어.
No,
내가 노트북을 보는데 먼저 엑셀 파일 보고 이 사람 얘기하는 걸 듣고 그걸 이해를 하려고 노력을 해야지. 엑셀 파일 보고는 보다 이 사람 그런 이유가 따로 다 있는데 내가 지금 그래서 물어보는 거야. 그렇잖아. 우리 기권
Okay, if we forget the moisture, let's forget first the moisture. If and I put some simplified numbers. If I have or how is it? Here. If I have or 75, go. I take a rounded number to explain. Coke 12. No, Coke 13 and
Coke 13.
and Dolo 12. And now, let's first forget the moisture. I want to know what is the proportion starting with 100 ore. So here, the proportion here is nothing less than 13 times 100 over 55.
네.
So it is no, 17, yes. Something like 17, we calculate. And here we have 12 times 100 times. And this is 16. Okay?
Yeah. Yes.
And actually, what is done here is it is corrected. Okay, I have to think about. Yes, it is this corrected by moisture. This is dry. You agree? So it is
Yeah.
the dry part, and over this is wet, and this is with a dry part. So it is just both correction of moisture. Maybe you should check this separately, and maybe we come back later on if it makes a problem. But we should move forward. Because what I wanted to tell you is this is something I have added. I have not on every Excel sheet of balance. It's just to have as a reference the data that you give me. And if a customer gives you data of his material, you should, you will, this is a preparation of data, there's nothing else. It's a standardization of data that the customer gives you. But this you may do differently depending on what he gives you. No, let's move to the first very important thing. I will reduce it a bit. Yes. That's okay. Here, all this is a presentation of the analysis of the ore. And what is done is that the analysis is presented in front of all the usual elements that we have. Of course, I did not put all the elements of the periodic table. The rare earth are not there, and selenium is not there, and because it's not necessary. The main elements present are there. And you can see that they are classified in the order of oxygen affinity. If you remember, you have here you have magnesia, yes, magnesium, aluminium, silicon, vanadium, potassium, calcium, titanium. And then you have the medium elements which have a medium affinity with oxygen, and which are the three elements that commonly share themselves between metal and slag. These are chromium, manganese, and iron. And then you have the elements having not a strong affinity, having a weak affinity with oxygen, cobalt, nickel, molybdenum, copper. And then you have two special elements. I put them separately, lead and zinc, because they have a very special behavior. They are gasified. When they are reduced, they fly off in form of gas. Okay? This part of the sheet is you must go through. You cannot just say, I accept the analysis that somebody gives you, because it's too important. The analysis will be the main base of your calculation, so you have to verify if the analysis makes sense, if it is consistent. So what we do here is to verify the consistency of the analysis. Now, let's move forward. These are the elements, and now we say these elements will be present in the ore. They may be present in 3 forms, in 3 families. They may be present, but that's not the case for the ore, in form of metals. But in case of the ore, it's not the case. You understand what I say? You cannot have in an ore, you cannot have manganese metal or iron metal in form of metallic iron. This is important that you understand. Manganese metal is metallic manganese, which is already reduced. And so this, if you had manganese metal and Fe metallic, you already had a part of ferromanganese in your ore, which is not, this doesn't exist. However, if you recycle some residues, you may have some, residues, including partly metallic manganese or metallic iron. And in this case, you should put numbers in this column, because this first column is relative to the metallic form of metals, or the pure form of the elements. And the second group of column is relative to oxides. You see? M for metal, O for oxygen, and you have each one is present in form of oxides. And of course, in the ore, we mostly have only oxides. All elements are under the form of oxides. Then you have a third group of columns. These are the columns of sulfides, so the combination with sulfur. And in our case, we don't have this. In specific cases, you may have sulfides. If you have an ore with high concentration of sulfur, you must think that at least one element or 2 or 3 are present in form of sulfides. Then you must fill out something here. But today it's not the case. We don't need to use this. The iron ore, the manganese ore, the nickel ore are oxidic, meaning they are composed of oxides. Okay, so what we do then is that we fill the columns with the figures of analysis that we got. First, I confirm there is no iron, no manganese metallic, so here all this is 0. Then, of course, we will fill all elements in the columns of the oxides, and here you can see something. This is something I had to change specifically for the ferromanganese, because generally except for manganese ore, manganese oxide is referred as being MnO. In all residues, in all slags, manganese oxide is MnO. It's only in the, let's say, fresh ore that you have MnO2. And then I already told you that the MnO2 oxide is easily reduced in MnO. But in this case, you better put two lines for the manganese, one line MnO2 and one line MnO. And you see that to well check the analysis, we have expressed each oxide as it is present. Meaning, if you have sodium Na, the oxide is Na2O1. Of course, we don't say Na2O1, we say Na2O. Magnesium is MgO, aluminium is Al2O3. Silicium is present as silica, SiO2. So I think you understand. We just have put the formula of the oxide. And this is the first check. You will check, does my element, does silicium, for instance, really, is it present in form of SiO2? Yes, in case of silicium, there is no doubt. In case of manganese, there was a question, but generally in the fresh ore, it is present in form of MnO2. So, what? Now it begins. The analysis we got is that we have 47.4% manganese in the ore. The data you gave me was not 75% MnO2, it was 47% manganese. And then, what shall we do? We are sure that manganese is present in form of MnO2. We know that the amount is 47. And then, you see, in this case, we don't know this number, but it's either you calculate it separately, but the best is that you try. I try 70, and then I see that the amount of manganese contained is 44%, just because in this column, this is a calculation column, I calculate the amount of element, of pure element included, and you see the pure element included manganese, then in case of manganese, is the manganese metal, which is 0, plus the manganese from this, and here I multiply by this number, by the molar mass of Mn, this one, 55, plus and divided by the molar mass of the oxide, and then plus some something if we have something in form of sulfide, which is not the case. But this, I recalculated at the board. I just say that if I have 70% MnO2, I want to calculate the amount of Mn. This is the amount of Mn is 70 times so Mn is 55, yes, plus 2 times 60, so it is 97, and so it is times 55 over, and this gives me 44.3. Of course, if I have some metallic element, it will be added, it will be included there. But the analysis that you get is the total manganese element. So you understand this calculation. All are similar. So in this case, I say, oh no, they give me 47, so I will increase here 74. It's not enough. 75. So it's okay. 47. That's the value they give me. You understand? And this you can do for I don't remember for silica. What you give me, I'll check, is 8%, or did they give me the silicium? I don't remember. You understand? People give you, when they give you an analysis, they give you either the metal or the oxide. If they give you the oxide, they give you 8%. You put 8%. Of course, you have no testing to do. If they give you 3.7% silicium, again, you will try, and you will say, I try with 10, and I see, no, it's not the good value, so I put 8, and so I find out what they give me.
You need this kilogram.
Sorry? Yes?
You need this
Yes,
kilogram.
yes, yes. But this method is, I think, is understandable, and it is useful for any people using an analysis. And this I teach to all the engineers I had over more than 30 years, and because it's really the base to understand if an analysis is good or not good. Because doing this, so I did the same for iron. They give this number for iron, and the iron oxide is this. Yes, in case of iron, it's also that you have two possible. You have Fe2O3 and FeO, but of course in the ore you have Fe2O3. And here the iron, we put it here because we have two lines as well. And Okay, these are the two main elements, and then you have SeO2, and you have Al2O3, and you have MgO. And when you make the addition, you see that you have, this is the sum of this column. This is the sum of the oxides, it's 93.2. If you make the sum of the elements, see, silicium, aluminium, manganese, iron, you have 57. And this column is actually the difference is the oxygen contained. For it, you calculate the oxygen content. And for instance, let's say for SeO2, if we have SeO2, you see Se is 28. So 28, O2, 2 times 16, the total is 60.
60.
So if I have SeO2 8%, so Se will be 8 times
60.
no, 28
28
over 60. And it's just, this is just that. You take this number, the 8%, you multiply by sorry.
Oxygen.
By, yes,
I
2 I. No, this is the, excuse me, this is the oxygen, therefore. Okay, here you have, of course, the silicon metal, which is 0, plus this number, multiplied by the molar mass, the 28, times 1, divided by the molar mass of SeO2, which is 60, which has been calculated here. And this is for the sulfides, it's 0 as well. So this cell is doing just what we did here. Okay? So this is not really not complex, but it is useful to do it, because what is the result? I'll tell you the result of that. The main result of that is that we obtain the sum of the oxides, and also, you see, of course, if I add then the elements and the oxygen, the sum is again the same, of course. This is because first I spread the metals and metal and oxygen, and here I am again make the addition, so it's the same. It's a check. It's a check. And obtaining 93.2%. What does that mean? Okay, for me, this means that the analysis is not very accurate, and it is not very complete. But once you have more than 90%, it is acceptable. Because, you know, in real life, there is no analysis that is perfect. It is very seldom that when you add all people give you in an analysis, it is seldom that you have 100. Okay, if you have much more than 100, it's not good. If you have less than 90, it's not good. If you have more than 95, it is excellent. Because perfection normally doesn't exist. And for me, in this case, this means that since the analysis comes from people working in the ferromanganese domain, I mean, normally they know how to analyze the manganese, and their analysis procedure will be correct for manganese and for iron. What maybe they don't analyze each time are the, let's say, the small oxides. You see, maybe they did not analyze Na2O. Maybe they did not analyze K2O. Maybe there was a little bit titanium included, titanium oxide. Maybe. Okay, they did not analyze it. And so, there are two conclusions. The first one is maybe the analysis is not complete. And the second one, maybe the analysis, some figures are a bit underestimated. But once you have more than 90%, it's acceptable, you can continue. If here you have only 80%, you'd better not to calculate too much, because there is really, you imagine there is 20% of the stuff you don't know what it is. Okay. Then there is one other point that may be, you may have some carbonates, meaning instead of MnO2, you may have no, this is hydrates, but the hydrates you eliminate when you're dry. Carbonates are like this. This may change also the result. Because you see, actually the mass spectroscopy measurement gives you the manganese, and it doesn't really tell you, except if you do another analysis at the same time, which is fluorescence X. It doesn't say you, it doesn't tell you surely that it is MnO2. So you may have a part of the oxygen in form of carbonates. And, but if you have this, it is easy to control and to test doing, how do you say in English? You know, when you burn, when you heat up to 1,000 degrees, these are destroyed. When you heat up, it gives MnO2 plus 2CO2, the gas that escapes. But, I mean, this is not dramatic, because this means just that, you know, in the upper layer, when the material is heated, in the very upper part, it will escape some CO2, and then you have the MnO2. Okay, it is slightly requiring slightly more energy to break this additional link, but this is not, it can be neglected in the first time. I just said you, it is an explanation for which you may not have 100. The explanation is that some measurement is not accurate. The other one is that you have missed some titanium oxide, maybe. And the third one is that instead of having the simple oxide, you have the oxide in form of carbonates, which includes some CO2 that will escape very soon. Okay.
Shall we have take
Quick.
a coffee break?
We can have a break. Also, but just tell me if this part you understand up to know this one. If you understand, or shall we afterwards come back and?
Yeah, so
지금 여기 답변은 모으는 거잖아. 이거 중요한 거고, 그렇지?
네, 맞습니다.
근데 이제 그 어디 저기 그건 난 뒤에 설명줄 거거든. 잠시만. 잠을 못 자가지고.
I can tell you, this is for people, when people teach mass and energy balances, this is unconventional to begin with this. People sometimes ask, but what is he doing? That's an analysis problem. But I can tell you, all engineers that got this, that learned this, afterwards they came to me and said, thanks to this step, we avoided many mistakes. Because when you get an analysis, you don't know if the guy giving the analysis did a mistake by writing down. You don't know if he was ill when he take the analysis. You don't know, and this is just a check. It takes you just few minutes, but it is very useful to avoid that everything is false afterwards. Okay, let's take a little break.